for the invitation to talk about machine learning in accelerated research. This is part of a work co-written by Clemence Cavalles, and also most of the APGene team collaborate in some way with this research. I will ask Clemence if you can introduce our challenging.
Hi, everyone. I'm just jumping in Ian's presentation to give you some context for this study. So dementia is a very frequent and progressive disease that is characterized by a decline in cognitive functions that exceed what we expect from normal aging, and also that has significant consequences on daily activities. And for Alzheimer's disease especially, it is also characterized by a long preclinical period where several biomarkers will develop for 10 to 20 years before the first clinical symptoms appear. And as you can see on this figure, we have an accumulation of beta amyloids in purple, for example, and for tau protein. However, this higher accumulation of biomarker does not necessarily lead to dementia. Therefore, we need additional tools to improve detection and prediction of the disease.
Thank you. So, as Clemence has said, we have a longer preclinical period for dementia and Alzheimer, and we already observed that sleep and physical activity are deteriorated in the dementia patients and also in the preclinical period. So our aim is to develop some digital markers that we can better predict dementia, even with the already known risk factors, and these digital markers are part of a sleep-wake cycle. So by sleep-wake cycle, I mean it's an umbrella for 4 domains: physical activity, rest activity rhythm, sleep, and chronotype. Chronotype is the timing we do things. For example, we go to the bed, we wake up, our main activity during the day, the timing during the day. And how we can answer this, we can directly ask people how much physical activity they do. But then we have the answer bias. For example, if you ask Severine how many times she do physical activity during the week, she will ask, okay, I cycling 3 times last week. And then we ask Francois, and he says, I climbed the stairs to arrive to the office last week. And we all know, well, everyone that works in Vilma knows that the lift was not working last week, so both of them have climbed the stairs. In case someone's recording, these are fictional characters, just to illustrate. But instead of ask them, and we can avoid the answer bias, give them some wearable device like accelerometers, so then they can put in their wrist device, use for 1 week, and then give back by mail. And then we have this nice time series showing the physical activity and the sleep patterns of them. Very well, but then a time series is maybe not the most intuitive for clinicians and patients, so we can summarize this time series in some variables that are more intuitive and more easy to interpret, and that are part of the sleep-awake cycle, so the 4 domains, daytime activity, rest activity, sleep. For example, we have 10 metrics just for sleep that are, of course, how long was the sleep, but also how many interruptions, how many times people have wake up during the night, or also the efficiency of this sleep. And daytime activity, we can have different thresholds of intensity of physical activity and how often this happens. And we extract and transform these variables using a free software GGIR. However, these interpretable features and metrics, they are very correlated. You can see that we have blocks of high correlation, and correlation is always a problem for most of statistics methods. will lead to multicollinearity. So what we can do? Of course, you can do PCA. I imagine that almost 9% of you or more know PCA, just to refresh our memory of PCA without using equations. So what we do in PCA, we have 2, 3, 10, 100 variables, and they are correlated. So there is a dispersion between this data in x1, x2, and also the other axes that I'm not showing. And then we create a latent variable, a new component, P1, and this P1 is a linear combination of the previous axis, and we are maximizing the variability. And then we create a second component, also a latent variable that is orthogonal, and maximize what is the residual of this variability. Then by construction, the variability of P1 is higher than P2 and higher than P3 and so on. And the correlation between P1 and P2 is 0, which is a good property. It's convenient to using another method. But we can do directly something else. We can do PLS. So what is PLS? I show you the same dispersion of x1, x2, but now in 3 dimensions. So imagine that this figure that I use ChatGPT to create, no, of course not, is in 3 dimensions. You can see the same dispersion, the same correlation, but then instead of maximize something between x1, x2, x3, we want to see the correlation of x1, x2, x3, x10, 100 with our outcome y. So here's y, and then we see the projection of the circles in ellipses, and instead of looking for maximize the variability, we want to maximize the correlation of a linear combination of all our axes with our outcome y. So we create this new component that maximizes the correlation. This is really interesting because now we have the better correlation between our axis set and y. So it's a natural candidate to predict y. And well, there is no property of correlation of x and P1, but the correlation is decreasing by construction. So the correlation between y and P1 is higher than with P2 and so on. Okay, we can also do sparse PLS, and then it's almost the same, it's just that now we are forcing part of the coefficients to be 0, and then this is saving our brain in the point of interpret the results, because then now we don't need to interpret all the variables, all the features, but only the ones that are non-zero. You can think about your research and think, okay, maybe I can try PLS too, but then we have some limitations. As you see, y must be something continuous, but of course the family is enlarging, and we can also have SPLS dA and dr, that when we have y that is binary or time to event, as in survival analysis. The only trick is that instead of using y directly, we are using the residual, or a small trick of the residuals that is outside of the scope of this presentation, but we can pretend it's the residual. Okay, so for our problem to predict dementia, we are going to training our cohort that is UK Biobank, and we are using SPLS dr to predict time to event for Alzheimer's dementia, and we need to set 2 tuning parameters. The tuning parameters are tk, number of components, and eta, the sparsity of the model. So eta ranges between 0 and 1, and closer to 1 is more sparse. So we set components 1, 2, 3, and a grid between 0 and 1. And we are comparing as a reference a model that is a Cox model using no risk factors. And from this model with the no risk factors, we have a syntax. And we are comparing with a model where we have components created by SPLS-dr and the no risk factors. And we want an increment of the syntax of 0.001 and that is significant. So we have all these combinations of components. So we have 60 different model candidates, and they are fighting to be better than the no risk factors. And as I said, significantly, it means that we need to do some cross-validation or bootstrap. So this method was originally proposed for cross-validation, but we see that this gives some instability to the model, so we propose the asymptotic confidence interval. And here the result for UK Biobank. We can see that for one component at the left, none of the candidates is higher than 0.01 of increment, but for two components, we have a large eta, 0.85, that is already higher, significantly higher. So this is good because it's relatively sparse, so we don't have so many features that will be selected, and we have two components to explain the new prediction. So how they look, these two components. The first component, you can see that is mainly daytime activity, so MVPA is moderate and vigorous physical activity. And component 2 is more related with sleep and chronotype. So these are the weights of the components that we are using to predict dementia. Okay, so as we use it, UK Biobank as the training cohort, it's our internal validation, and we see that it's increasing the index significantly, even with one component when we add to the no risk factors. And in our external validation white hole, also the index is increasing when we add the two components, compared with a model with all the no risk factors. Okay, so this is a secondary analysis when we put not only the no risk factors, but also biomarkers and cognitive tests. So as Clemens has said at the beginning, we can observe beta aminoids and PTO that are accumulate, and here we are putting in the model the PTO protein. So we are doing harder for the model to increase the prediction performance, even with these good predictors of dementia. Good. We hope this is going to be published soon. So what is next? We know that accelerometers in the wrist, but also in the ankle can, for sleep is better the wrist. So we can identify awake and sleep stages using accelerometer. But if you want to go deeper in sleep, then maybe it's not enough. We need PSG, polysomnography, but polysomnography can identify REM and non-REM sleep at the cost of many wires and devices, and people must go to a lab to have an evaluation. We cannot have a PSG at our own home, and so it's not realistic with our habits of sleep. So can we do removing part of these cables? And well, we can. We can use only the EEG, that is this part of the PSG that is in the head, and we can use a band head that can collect most of the part of the EEG, so can give the information about REM and not REM sleep. Of course, has more error than the complete PSG, and also can record the motion of the head. So it's similar to the accelerometer. Of course, it's not measuring the acceleration of the wrist, but the head. And except if you are dancing a very exotic dance, is much more subtle. So we are losing our knowledge of thresholds and so on that we know for the ankle, for the rib, and for the wrist, now investigating the acceleration on the head. But we can cross these two informations and try to identify RAN behavioral disorder, that is another disease that we want to investigate. Thank you so much.